In this video I want to talk about how we can add 1-bit adders that I talked about before and create multi-bit adders. So there are three types of multi-bit adders, or more specifically carry propagate adders. So we can have the ripple carry adder, which is slowest. We can have carry look ahead adder, which is faster than ripple carry adder, and also we can have the prefix adder, which is the fastest among these three types of carry propagate adders. So carry look ahead and prefix adders are generally faster when we want to add numbers that have more number of bits, usually greater than 16 bits. But they also require more hardware too. So there is a balance that needs to be kept, whether we want to use a ripple carry, which is slower but it requires less hardware, or a carry look ahead or a prefix adder, which is faster but it requires more hardware. But generally speaking, the general symbol for a multi-bit adder looks something like this. We have the carry in. From the right, we have A and B each being n-bit numbers. We calculate the result of summation, and then we have a carry out at the end too. So let's just take a look at one example. Let's just say we have number A to be 1011 and number B to be 0111. So I want to add A and B together. So we have 1011 and then 0111. And for this one, we don't have any carry in from the previous stage. So this carry in is going to be basically 0. So we have 1 plus 1, it is 1, 0. We have 0 here, 1 carry to the next stage. 1 plus 1 plus 1 is 1, 1. So we have 1 here, 1 carry to the next stage. 1 plus 0 plus 1, it is going to be 1, 0. So 0 and 1 carry to the next stage. And finally we have 1 plus 0, which is basically 1, 0. So we have 1 and 0. So these 4 bits are the summation result. This is the carry out that we produce, and this is basically the carry out that specifies whether we have overflow or not. And for this example, the carry in was basically 0. So if you look closely on the way that we calculated this summation, is we started from the least significant bit, we added the 2, we created a new carry, and then we considered that for the next stage, and we repeated this process. For the first one, what we had was only 2 bits that needed to be added together, and that is what we can do using a half adder. But for the other ones, we definitely needed to have a full adder, because we had to find out the result of adding 3 numbers: the carry from the previous stage, the corresponding bit from the first number, and the corresponding bit from the second number. So to make everything consistent, what we can do is that we can implement this addition circuit by considering 4 full bit adders. What we only need to do is that we need to make the first carry in signal to be 0. So this is an example of a ripple carry adder, in which we chain 1-bit adders together, and to calculate the final result, we basically perform this 1 by 1 by 1 by 1. Of course, when you have all of these things together, you cannot control that this one performs its functionality first, and this one second, and this one last. What happens is that you have some intermediate result for the values for S1 all the way to, let's say, S31, assuming that this is a 32-bit adder. And that is because each one of these things can produce the result, but also the final result depends on the carry from the previous stage. And as you can see, this carry is basically rippling through each one of these levels. And that is why this is called as a ripple carry. So for the final result to be available, the carry signal has to go through all these stages, even though the individual bits are only going through one stage. So because of that, we have the disadvantage of being very slow in comparison to the other types of multi-bit adders that we can have. So how slow you can say? The total amount of delay that we have for a ripple carry adder is n times the amount of delay that we have for a full adder. And n is the number of bits that you have for the full adder. So if we want to add two 32-bit numbers, this n is going to be 32 multiplied by the delay of a 1-bit full adder. But there are ways to predict the value for carry even before the result of summation for each one of these individual additions is being finalized. And that is what we want to use to be able to predict carry and produce the final result faster. So the reason that large ripple carry adders are slow is that the carry signal must propagate through every bit in the adder. So that is the main reason that we modify the design and create carry look-ahead adders, which are able to predict if we have a carry signal or not. So a carry look-ahead adder solves this problem by dividing the adder into blocks and providing circuitry that quickly determines the carry out of each block. It is said to look ahead across the blocks rather than waiting to ripple through all the full adders inside the block. So now let's just see how carry look-ahead adders work. So if you remember before, for a full adder, we had these two Boolean functions. So for the result of summation, it was A XOR B XOR C in, and all of these variables are single bit. And for the carry out, it was AB or AC in or BC in. So as you can see, for calculating S, we need to have a 3-input XOR gate. Or if we don't have access to that, we should implement it using the result of the sum of product, which required us to have 4 3-input AND gates followed by a 4-input OR gate. For the carry out signal, as you can see, we require 3 2-input AND gates and 1 3-input OR gate. But let's just see what happens with individual bits. So let's just say we have only 2 bits inside a number. So let's just call these whole numbers A and B. So don't confuse these A and B with these ones. So these are basically 1 bit. But these numbers are actually having 4 bits. So in the middle of this number, right? And we can have it as more than 4 bits. So in the middle of this number, let's just say we have bit AI and bit BI. So even though we may not know what are the values for the previous bit or the bit after that, we know that if A and B, or if AI and BI are both 1s, we generate a carry. And this is not dependent on the values before AI and BI. Also, we know that if either of AI and BI are 1, we may propagate a carry if Cin is 1, or basically if the carry in from the previous stage is 1 and one of these things is 1, we actually propagate this carry in to the next stage. So this is the basis for the carry lookahead adders. So for example, for checking if AI and BI are both 1, what we need to do is we only need to check AI, BI. Basically, if the AND of the two is 1, that basically we can say we are generating a carry. For the second one, we only need to check AI or BI being 1. Again, as you can see, just by a simple OR, we can check whether we are propagating a carry from a previous stage or not. So now if we want to put all of these together, we can say for each stage, so CI, either we generate a carry, basically AI, BI, or we propagate a carry from the previous stage, AI or BI, being ANDed with the carry from the previous stage. So as you can see, the carry for this stage is 1 if both AI and BI are 1, or if one of them is 1 and the previous carry is 1. So this is the basic concept behind carry lookahead adders. So let's just go over the definitions one more time. We say that column I produces a carry either by generating a carry itself or propagating a carry from a previous stage. So based on this, we create two signals for each individual sets of bits. We call one the generate signal, which is the result of ANDing the corresponding bits in the two numbers that we have. And also we create a propagate signal, or we call it PI, which is as a result of ORing the corresponding two bits in the two multi-bit numbers we have. So the carry in each column can be calculated as the OR of the generate signal and the AND of the propagate signal multiplied by the carry from the previous stage. Or we can just simply say carry in stage I, or for bit I, is the generate signal for that bit, or the propagate signal being ANDed with the previous carry. So now you can see with these signals that are much computationally less intensive than the actual summation and carry out signals that we use for the ripple carry, we can at least have a good determination of whether a stage is creating a carry or not. So let's just go through the steps for a carry lookahead addition. First, we calculate GI and PI, or more specifically the generate and the propagate signal for all the columns in the number that we have. In step 2, we compute G and P for a k-bit block of bits. And then for step 3, the Cin propagates through each k-bit block, each one having a propagate or generate signal. So let's just see what happens if we have a 4-bit block. So if you remember from the previous stage, we had previous slide, the general signal was Ci to be Gi plus Pi multiplied by Ci minus 1. So let's just assume we want to do the calculation for a summation of two 4-bit numbers. So this one is 4-bit, this one is also 4-bit. So we have A we have B, the bit numbers are A3, A2, A1, and A0, and this one is B3, B2, B1, and B0. So the first step is to calculate the generate signal and the propagate signal for all of the columns. So GI is basically AI being ANDed with BI. So for each one of these, if we calculate the result of bitwise AND, we actually create the generate signal. For the propagation or propagate signal, we need to calculate the OR of these two. So we have AI or BI. Now we want to compute the G and P for k-bit blocks. So for doing that, what we basically need to do is that we need to repeat this process several times to get to the final equation. So if I have this value calculated for C0, basically the first set of bits, it's going to be G0 plus P0 multiplied by C in, basically the carry in that we have for the beginning of the process. So this should be C. Now to calculate the value for C1, we have it as G1 plus P1 multiplied by C1. So we just simply replace C0. We just simply replace C0 from the value that we had from the previous stage. So this becomes G1 plus P1 multiplied by G0 plus P0 C. For C2, we have it as G2 plus P2 multiplied by C1. And we do the same thing. We replace this C1 with the value that we have from the previous stage. So this becomes G2 plus P2 multiplied by G1 plus P1 multiplied by G0 plus P0 multiplied by Cin. And this process is going to be repeated to calculate C3 as well. So this is G3 plus P3 multiplied by C2, or being ANDed with C2. So that becomes G3 plus P3, G2 plus P2, G1 plus P1, and then G0 plus P0 C. So if you do these additions and basically these ORs and ANDs, what you end up with is, for the generate signal for the 4-bit block, we have it as G3 or P3 ANDed with G2 or P2 ANDed with G1 or P1 ANDed with G0. There should be another parenthesis here as well. And for the propagate signal for the 4-bit block, we have it as P3 ANDed with P2 ANDed with P1 and ANDed with P0. So let's say we want to create a 32-bit carry look-ahead adder, and we divide this into blocks of 4 bits. So in total we have 8 blocks, each being an addition, producing an addition of 4 bits. So we have the regular set of full adders, but for calculating the carry out, we don't wait for these things to be basically calculated one by one. What we do is that we add this additional circuit that calculates the carry out for us much faster than if we wait for these carries to be basically rippling through these 4 stages to be calculated. So each block has these 4 full adders in addition to this circuit that calculates the carry out of that block. So if we want to find out the delay for a carry look ahead adder, we have TPG. Basically that is the delay to generate all PI and GIs. If you remember, GI was basically AI ANDed with BI, and PI was basically the result of AI or BI. So since these can be done simultaneously, that is equivalent to only having the delay of one single either AND gate or an OR gate. Then we have the delay of the PG block, which is basically the delay that is as a result of calculating the generate and propagate signals for the full block. So in the previous example, since the blocks were 4 bits, that means that the delay that is caused by calculating the generate and propagate signal for that 4-bit block. And then finally we have the delay of the AND OR gate at the end. Basically it's an AND gate followed by an OR gate that is going to be added, because if you look here, we have the propagate signal being ANDed with C in and then being ORed with the generate signal to create the final value for the carry out of this stage. So usually what happens is that a carry look ahead adder is faster when the number of bits that we have for the two numbers that we want to add together is greater than 16. So if it's less than 16, it basically doesn't have any benefits, right? So generally, when the number of bits that you want to add together is greater than 16, then you can see the benefit of having a carry look ahead adder. So now the same concept can be further improved to create a prefix adder, right? With the carry look ahead adder, what we do is that we fix the size of the blocks that we have. So for example, in the previous example, we wanted to add two 32-bit numbers, and we divided the number into 8 blocks, each having 4 bits. But what prevents us from having smaller block sizes? So that is basically what is happening in the prefix adder. So what we do is that we create, generate, and propagate signals for blocks of size 1, 2, 4, 8, and so on and so forth, right? So by doing that, we can significantly reduce the calculation time even further. So in general, we have log 2, basically the log base 2 of n stages. So let's say if we have 32 bits, that means that we need to have 5 stages for a prefix adder, but that will worth it, as I will show you in an example. And the general design of the prefix adder looks something like this. So since the circuitry is a bit more complex, what we do is that we kinda shorthand it with some legend. So anywhere that you see a square block, that's basically equivalent for creating the propagate and the generate signals. Anywhere you see this black one, that is the equivalent circuit. And anywhere you see this rounded square, that is equivalent to this one. So as you can see, you start by smaller block sizes, and then you apply the same concept procedurally further and further until you get to larger block sizes. As for the delay for a prefix adder, we have the TPG. Basically that's the delay to produce the propagate signal and the generate signal for each individual bits. And then we have the TPG prefix, which is the delay of the black prefix cell and OR gate. And then finally we have the delay of the XOR gate that we have for the final stages. So here you can see that the delay is actually calculated as log 2 of n multiplied by t of PG prefix. So if you are adding numbers that are very large, the prefix adder is definitely more preferred. So let's just put some numbers into these equations and see how they compare. So here in this example, I want to compare the delay of 32-bit ripple carry, carry look ahead, and prefix adders. For the carry look ahead adder, I use 4-bit blocks. And then for the delays that we have, for the delay of a 2-input gate delay, so this is I would say a generic value, right? So usually it is a bit different for the AND gate and OR gate and XOR gate, but let's just assume that the delay of a 2-input gate is 100 picosecond regardless of the type of the gate. And let's just say there is the delay of a full adder is 300 picoseconds. What we need to do is that we just need to plug this number into the previous equations to find how much time it takes for each one of these multi-bit adder to calculate the result. So for the ripple carry, if you remember, the delay was basically the number of bits that you want to add together multiplied by the delay of a single full adder. So since we have 32 bits in our numbers and each full adder is 300 picoseconds, the total delay is 9.6 nanoseconds. So you can see it is very a small number, right? But just imagine that you want to do hundreds or thousands of these calculations per second. So then these numbers would add up. For the carry look ahead, we have the TPG, which is basically the delay of a single gate. For the TPG block, it is equivalent to a delay of 6 2-input gates. Then we have n divided by k minus 1, Tn OR gates, and then k multiplied by the delay of a full adder. So if we add all of these together, what we end up with is the actual value is 3.3 nanoseconds. So by just adding a little bit of more circuitry, we were able to cut the delay of the addition by 3 times. Now let's just see what happens with the prefix adder. So if I just plug the numbers here, in the equation that we had, the delay of the prefix adder is actually 1.2 nanoseconds. So almost an order of magnitude smaller than the result of the regular ripple carry adder. So you can only imagine if we have values of more than 32 bits, this difference is going to be much more significant. So what about subtraction? When we have a circuit for addition, the subtraction is very easy. Because if you remember from before, when we wanted to subtract a number from another one, what we only needed to do was to calculate the 2's complement of the second number. So a minus b, it's actually a plus negative b. So that means that if we have a circuit for addition, we can use the same circuit for subtraction as well. What we need to do is find the value b with a negative sign. So do you remember what was the procedure for calculating the 2's complement of a number? We basically had to invert all the bits and then add 1. So that's exactly what a multi-bit adder can do for us, right? So for inverting all the bits, what we need to do is that we need to have some inverters in the path of the input B. So let's say if B is 32 bits, we basically have 32 inverters that are each inverting 1 bit in the value B. So this is basically the flipping the bits part. But what about adding the 1? So adding the 1 can be done using the carry in input of the multi-bit adder. So if you remember, for the multi-bit adder, we said that it is good to use a full adder for all of the bits of the summation circuit or the addition circuit, right? But when we want to do the addition only, the carry in that we have for the first stage, we just put it as 0. But for doing the subtraction, what we basically need to do is that we need to calculate the value B with a negative sign. Basically, we need to make the sign negative. So that requires all the bits to be flipped as well as being added with 1. So flipping can be done using inverter gates. But that addition, instead of creating or using another multi-bit adder to do the addition, what we can do is that we can just put the carry in for the first or the least significant value to be 1. So this is basically connected to VDD, or its value is 1. So by doing that, what we can do is that we can practically use the same circuit that we use for addition to perform subtraction for us as well. I'm going to show later on how this can be useful when we want to design arithmetic logic units that are capable of performing several functionalities in one unit.